All right, any questions? Okay. Chapter 17,
We're not done with it yet?
we're done with it this way. I'm not going to review it though because I don't running behind schedule. So we're going to just start chapter 18 today. If there's questions about chapter 17, I can go back through.
Titration, the last part of 17?
Yeah, pretty much. It's titration. Just the three most important things. The three most important things were common ion effect, buffers, and titration. There's one other thing. There's the hydrolysis of salts. Is that it?
Isn't that running back to like the other chapter?
Yeah, that's more like chapter 11. And so we'll look at hydrolysis of salts tomorrow's lab.
So are we going to have the exam Wednesday, Thursday? Thursday.
Yeah. If we have the exam on Thursday, what I have to ask you to do is be prepared for lab on Tuesday. Normally I want to talk about the titration experiment beforehand, but I'm not really going to have much time to talk about it, so make sure you prep for the titration lab. I need to post this. I think we're going to switch pH meters to a different style pH meter. Tomorrow, have you guys used the LabQuest
Yes.
system? No. We're going to use it tomorrow. And so if it works well tomorrow, then we're going to use the same system on Tuesday for our pH titration. pH titrations, we're only doing, how many titrations? We're going to do 2 titrations or maybe more. But we're only going to be doing 1 pH titration because it's so time consuming. We'll talk about it then. We don't stop right at the end point. We just keep going. So if there are no questions, then I want to start chapter 18. Chapter 18, we have 2 new K values. There's something called KSP and something called KF. So the first half deals with KSP, the second half deals with KF. KSP, what this stands for is the solubility product. So let me talk briefly about solubility first. There are 2 main definitions for solubility. One is we have qualitative way of defining it. In our qualitative way of defining solubility, we have 3 categories. Soluble, or S. We have slightly soluble. Yeah, SS. And we have insoluble. Gets the symbol I. Got it. And so what do these mean? Well, it just means it's soluble or insoluble or somewhere in between. But it was defined back when you were studying the solubility chart. The way it's defined is that soluble means you can dissolve more than 1/10 of a mole per liter of solution. And so it has a solubility greater than 0.1 molar. Insoluble means less than 0.1 moles per liter will dissolve, and slightly soluble means about 0.1 moles per liter will dissolve. Now 0.1, is that a lot or is that a little? It sounds like a lot, right? And so if you have something that's like 0.09, it sounds like 0.09, it's a lot of moles per liter. But these are the cutoffs. And so we have different levels of solubility. For example, if something's insoluble, we want to know how insoluble is it? Is it borderline or is it extremely insoluble? And therefore we have a second definition for solubility, a more quantitative definition. In the quantitative definition, solubility, which is given the symbol, we don't want to use S because we already used it for soluble, right? But we're going to use S again. But it has a slightly different definition here, and so it depends on what context you're talking about, S. You know, S in the context of chapter 18 problems means this S, not that S. So the two different S's. This is chapter 18S. In the chapter 18S, the solubility is defined as the max amount of solute that will dissolve in a given amount of solvent. And so those types of things we can find in tables. Let's take a look. What do you think? Calcium fluoride. Calcium fluoride, let's do it. This one first. Calcium fluoride is soluble. That seems to make sense. Calcium fluoride should be soluble because calcium chloride soluble, calcium bromide soluble, calcium iodide soluble, and so calcium fluoride should be soluble. Then what we want to do is we want to think in terms of quantitatively how much will dissolve. And so let me just search calcium fluoride. Calcium chloride is an inorganic compound with the formula CaF2. It is a colorless insoluble solid. It occurs as a mineral fluorite, which is often deeply colored owing to impurities. And so impurities can dramatically influence the color. I mean, red lake, blue lake, those are all impurities. And those specific impurities color it a certain way. But here's calcium fluoride. When we look at the solubility, here it is. We have two solubilities here. We have a solubility at 18 degrees C and a solubility at 20 degrees C. 20 degrees C is closer to room temp, so let's look at this. Notice the solubility changes with temperature. The lower the temperature, the less soluble. The higher the temperature, typically the more soluble. And so we can dissolve. Now this solubility is a little bit different because this solubility is what we call molar solubility. How many moles will dissolve in a liter of solution? This solubility is totally different because this solubility is how many grams of calcium fluoride will dissolve in 100 milliliters of solvent, not solution. And the reason this solubility is so common is because it's an easy experiment to do. You measure out 100 milliliters of water and then figure out how many grams you can get to dissolve, crush it up, etc. And so typically when you see solubilities, they're in units of grams per milliliter of solvent. Now, if I want to convert that into molarity, how would I do that?
Times the molar mass.
Okay, well, we use the molar mass to convert grams to moles, so. And then would we convert milliliters to liters? Would that be it?
No, but then you add in the density of the water.
Yeah, exactly. This isn't a simple thing because this is milliliters of solvent, whereas this is liters of solution. And so it's different. This volume and that volume are different. So how do we figure it out? Well, we need the density. How will we use the density to do that?
Well, I mean, when you put put in the grams, then
Mhm.
it should affect the volume of the solvents.
It could affect the volume, so this is,
And so with this difference in solvent, we see that the volume of the, what do you call it, of the volume of the solute, and then since we know the grams before you put it in, then the correspond density.
okay, so if we know the volume before,
No, we know, if we know the grams before we put it into the solute,
Mhm.
and then we see that there's increase in the volume of the solute when it comes to solution.
Mhm.
The difference between those, that's going to be the volume of the solute. So with the graph from the solute, then we can find the density, right?
Yeah.
Yeah, right?
well, are you gonna actually, do you actually measure the volume? You would have to measure the
Yeah,
volume?
we have to measure the
You,
volume.
you'd have to measure the volume change?
Yeah.
Okay, no,
But
no. That's not the way, because the volume change could be very small and very difficult to measure.
All right.
And so this is what we're going to do with this. What we're going to do is somebody has to mix it up and then measure its density. And so what we're going to use is we're going to use somebody else's density to do that. And so what we'll do is, how much does 100 milliliters of water weigh? 100 grams. And then if you add in the solute, you're going to have 100.0016 grams total. And if you have 100.0016 grams total and you know the density of the solution, then you can figure out the milliliters of solution,
Okay.
total solution. And so that's the way we would do it.
Okay.
And so this goes back to, I don't know, chapter 5, something like that. But just to remind you, it's a little bit more tricky than doing a straight milliliter to liter conversion. But anyway, so this is pretty soluble. We said calcium fluoride is soluble.
Not anymore.
Not anymore. I mean, this is what? This is 1.6 milligrams per 100 milliliters. Is that very soluble? No. In fact, calcium fluoride is what we call insoluble. Calcium fluoride is insoluble. And so calcium fluoride is insoluble, which means that our solubility rules are, fluorides just mess things up because fluorides are going to have a lot more exceptions. And so this is why fluorides are left out. When you're looking at the solubility rules, it's chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. If you add fluoride in there, then you're going to have a heck of a lot more exceptions, which means more memorization. And is it really worth it? And so if you ever encounter a fluoride, the best thing to do is just go ahead and look up its solubility. Right? And then you can classify. And so we have the solubility here. It's fairly insoluble. But how does the solubility of calcium fluoride compare to something like silver chloride? Yeah, you'd expect it to be bigger. And so let's look at silver chloride. Silver chloride, we know for sure, is insoluble. And if we look at the solubility here, it's 520 micrograms per 100 milliliters, or 100 grams of water. And so 520 micrograms, that's not much, is it? 520 micrograms is how many milligrams? How many milligrams? 0.5. And so this is half a milligram. Roughly half a milligram. What was calcium fluoride? It was, what is it? Here. This is in grams, so to go to milligrams and multiply by 1,000, we were 1.6 milligrams. And so calcium fluoride is 3 times more soluble, but still you aren't going to get much, right, in there because we're talking about very minute quantities here. And so these are some examples of solubilities. What types of things affect solubility? How can I make it more soluble? How can I make it less soluble?
Changing temperature.
Changing temperature?
Sure.
It's going to change K. Changing temperature is going to be discussed in chapters 17, 18. chapter 18. But before we get to chapter 18, we're going to go back to chapter 14, 13, something like that. Chapter 14.
But we are on 18.
Are we on 18?
Yeah.
That's right. We're on chapter 18. The previous versions, if you're on the older edition, that's where my head is, in the older edition. Anyway, it's going to be discussed in chapter 19. So we'll look at that later. What are some other ways of changing the solubility?
We change the solvent.
We change the solvent, different solvents, like, for example, acetone. Is it soluble? No, it's insoluble. Totally. When they say insoluble, that means you can't even really measure it. It's too small to measure, let's say. Or maybe they don't have the data. It's going to be insoluble in acetone. So that. Although in chapter 18 we don't change the solvent. You know what we're going to do in chapter 18? The solvent is always going to be water. And so we aren't going to look at ethanol, we aren't going to look at acetone. Are there any other ways?
Change the pH.
We can change the pH. Changing the pH could change the solubility. Not for everything, but for a lot of stuff. So here it says slightly soluble in acid. And so this is going to be a big kick to its solubility if we put it in acid. Right? Now, why is something like this? Oops. I didn't write it there. Why is something like calcium fluoride more soluble in acid than in just plain old water? Does that make sense?
Maybe because of the theory with the pH change?
This goes back to the last test. Last test. Which one is most basic? Sodium chloride, bromide, iodide, fluoride, hydronium. Which one was most basic? Fluoride. Fluoride's different. Fluoride's different than chloride, bromide, iodide. They're all neutral. Fluoride is the odd one out. Fluoride is actually a base. This is something this is a pattern that you'll see. If you look at something like this a lot, iodide, bromide, chloride, they're all clustered together here. The fluoride is way, way more basic. So considerably more basic than the other species. So, its solubility is different than the other species. The acidity is different. It's just different. And so that might give you some clues. But, in this chapter, we're going to be examining that. Not only do we want to say it's more soluble in acid, we want to calculate the difference. What is the difference in solubility of calcium fluoride in water versus acid? And it depends on what pH acid it is. What is the difference in water versus pH 6 acid, pH 5 acid, pH 4 acid? And so those are the types of calculations we're going to be doing in this chapter. We're going to be looking at solubility and pH, and also there are other ways. Let's say I had some calcium ion. Would I be able to precipitate it out with fluoride? Yes? Yeah. You used oxalate in the lab, but you could have used fluoride. I don't know which one's less soluble. We could look that up. But we could have precipitated it out with fluoride. And so, what factors influence that? Should we precipitate it out with the oxalate, or should we precipitate it out with the fluoride? Why oxalate? Why not fluoride? Fluoride's unstable. Fluoride's very stable. Remember the conjugate relationship. The conjugate relationship is the extreme Like, for example, fluorine is extremely reactive, means its conjugate is extremely unreactive in redox. That's redox. The danger of fluoride is not redox. What is the danger of fluoride? Do you know why some people don't like fluoride in their drinking water, or people don't brush with fluoride toothpaste or stuff like that?
Wait, didn't you tell us a story about like there was like the fluoride people, like they have that handshake or something,
That's
right?
the fluorine people.
Fluorine.
The fluorine people have the fluorine people's handshake. The fluoride people are different, though. The fluoride people and the fluorine people are totally different. The fluoride people are kind of stable. You know, the fluorine people are the exciting ones. They're the less stable ones. Yeah, I did talk about that. The fluoride is, that's for redox, right? Fluoride is totally stable. Fluorine is totally reactive. But the danger with fluoride, I'm not saying fluoride is stable. Fluoride is stable in terms of redox reactions, but it's unstable in terms of metathesis reactions, because it likes to precipitate things like calcium. And you need calcium in your body to, you know, what happens if you have too little calcium in your body?
No hair.
Heart failure, right? Right, two-year-old hypocalcemic. Remember that? Did I show you that?
Yeah.
But they got rid of the calcium using EVTA, but you could get rid of the calcium using fluoride. Right? You wouldn't want to inject fluoride then. Anyway, or teeth. You know, if you think of teeth, what are teeth made out of? Calcium. And why do they use fluoride in toothpaste? Precipitate out. Well, actually, it doesn't really precipitate. It exchanges. You know, there's a hydroxide ion in the mineral that makes up your teeth, and you replace it with fluoride. It makes it much more stable. It's less reactive. And so, anyway, in this chapter, we're going to be looking at all kinds of stuff related to solubility. You know, how to control things like dissolution, which is dissolving, and precipitation. So let's take a look at KSP right now. The first thing we're going to look at is something called the KSP equation. The KSP equation is always going to look the same. So for example, if I wanted the KSP for silver chloride, the equation looks like this. We start off with silver chloride solid, and then this goes to silver ions, AQ, and chloride ions, AQ. And so if we look at the forward direction here, the forward direction is what we call dissolution, or dissolving. And so this is taking some solid silver chloride and dissolving it. Is silver chloride 100% insoluble? No, I mean 520 micrograms will dissolve, so a tiny bit of it will dissolve in water. If we look at the reverse process of this, the reverse process is what? Excuse me, called what? Precipitation or crystallization. That's the reverse. And so we're always writing the dissolution equation regardless of if we're looking at a precipitation. If we're doing a precipitation problem, we still write it like this, but we just think of going backwards. And so there are two directions in a KSP equation. Typically when we go forward, we're looking at how much dissolves, right? And how much dissolves is called the solubility. And so when we go forward, we're looking at plus S. This saves us a little bit of work because then we don't have to relate X and S, right? And so this would be plus S molar, plus S molar. This is dissolution or dissolving. And it's going to reach some sort of dynamic equilibrium where what we've done is we've saturated the solution with solid. We can't dissolve anymore because it's unsaturated and we've reached this equilibrium. If it's unsaturated, then it's just going to continue to dissolve and not be there. When we're dealing with precipitations, we're going backwards here, and we don't care if we go backwards or forwards because it doesn't really matter, right? And so it's better not to flip the equation, because if you flip the equation, what do you have to do with k? When you flip the equation, you have to, what do you do with the k value? Can you use the same k value? No. Do you take the negative of that k value? No, you have to invert the k value. Inverting the k value is a pain. Why do it? You know, it doesn't matter if you go left or right, does it? No, so we always write the equation the exact same way for any problem, precipitation or not. And so here, what do we have? Do we have minus S, minus S? No, S is the amount that dissolves. So if we're precipitating, then we call it X. So this is going to be minus X molar, minus X molar. That would be a precipitation. And so here's our dissolution. When we're looking at dissolution, we dissolve it to a max. Here. When we're looking at precipitation, we're losing whatever we had, you know, started with, which may or may not be S. You know, it can't be S because S is saturated. We'll end up at S. And so when we're looking at this equilibrium, then the KSP is just the K, the equilibrium constant for this, and that's just equal to the silver ion concentration over the chloride ion concentration. Do I include silver chloride in here? No, silver chloride is a pure solid, so we don't incorporate that. And so this is why it's called the solubility, because it talks about solubility and precipitation, and it's the product because it's the product dissolution, or it's the product that is you're multiplying these concentrations in. All right, now what can we do with this? Well, what we can do with this is we can relate KSP and solubility. That is, normally we find KSP values in books like this, or tables. Here's the solubility product. KSP is 3.9 times 10 to the minus 11 for calcium fluoride. For silver chloride, it's a different number. In fact, well, let's get the numbers here. We have to do this in the morning, but I should do this in the afternoon for you guys. Let's get the wood figure out of here. So if I look at the KSP for silver chloride, I'd see that the KSP is not here.
Not there.
I think I remember it. 1.8 times 10 to the minus 10. But I have to verify that. Does somebody have their book?
1.77 times 10 to the negative 10
1.77 times 10 to the negative 10.
at room temperature.
Okay, our book will round that off. And so this is 1.8 times 10 to the negative 10. And I forgot to mention this in the morning class, but one of the things we can do is we can look at the solubility product and try to predict the solubility. So this one has a KSP of 10 to the minus 10, product of the ion concentrations. This one has a KSP of 10 to the minus 11. Okay. So which one's more soluble? This one, this bigger KSP, or this one, smaller KSP? Which one's more soluble? The bigger one, right? The bigger KSP, except that it's not always so simple, because the relationship between solubility and KSP is not linear. It's not linear because, let me show you that relationship here. And so here, if we look at this, silver chloride solid, and we're going to keep this simple here. That is, we're going to assume that nothing's dissolved. Silver chloride we ignore, so this is 0 molar and 0 molar. And then there's going to be a change. So the silver chloride, we're going to get to dissolve. We're going to dissolve the maximum amount, so we get the maximum amount of change. And that's going to be plus S or plus X? Plus S molar, plus S molar. The maximum molarity we'll get will be S. And so the KSP up here, this is going to be equal to S times S, which is S squared. Now, if we go to calcium fluoride, what is the KSP equation for calcium fluoride?
Goes from CaF2 into Ca2 plus and then
CF2 solid to
Ca2 plus and then 2F minus. So then we get.
All right, let's stop here. This is the correct equation for KSP, assuming what?
It's completely ionized.
It's completely ionized. That is, there are no, what? Well, there's going to be, there's no, oh, you're saying calcium fluoride molecules?
Yeah.
Okay. Yeah. And so we're assuming what?
Complete dissociation.
Complete dissociation. We assume ideal behavior. What happens if it's not behaving so ideally? What can happen when it doesn't behave so ideally? What might we expect in non-ideal behavior? Well, let's say there's no complex here. Let's ignore the complex for now. Complex formation does occur, but that's not behaving non-ideally. I mean, we should be able to predict. Maybe there's a complex that forms. In fact, I might expect calcium fluoride to deviate more than silver chloride. Deviate from ideal behavior. Why? Why might I expect calcium fluoride to deviate more than silver chloride? Maybe. Maybe not,
It's electron density.
Not electron density, close. We don't use the word electron. Use a different word.
Charge density.
The charge density, right? The charge density on calcium is,
0 plus.
yeah, which would compound what? Which makes what worse? You have a 2 plus charge, what becomes worse? Well, let me give you a hint, and sorry if I get the chapters wrong, but it's the last chapter in Chem 1A, which was what, chapter 13? Last chapter in Chem 1A.
The orbitals?
Was it the last chapter? Maybe second to last chapter? I don't know. Look. I asked you to read it. It was only one page long, one page of that chapter. I asked you to read it near the beginning of the semester. But it's easily forgotten, right? It was a long time ago, the beginning of the semester. We talked about it at the beginning because we were discussing concentrations, right? Ideal solutions versus real solutions. In ideal solutions, we ignore the. All right, I better stop this because this is how I get so far behind. You're right. We ignore interionic attractions, right? So there's no ion pairing, and so what happens is, we assume ideal behavior. So these should be totally independent of each other, and there should be like a calcium ion sees a fluoride, they can't pair together, for a moment of time. So do you guys remember that chapter 13, Van Hoff factor, activity? And so we're assuming that these are ideal.
Wait, so what does charge density mean?
Charge density? Why is charge density a factor? Well, there are two things. One, you could just look at it because you look at a table, you see it a bunch of times, and you'll see a pattern in that table. And then once you see the pattern, then you try to start to understand that more theoretically. And so, since you asked, then I'll spend a little bit more time on this. But sorry, not much more time on this because I don't want to. Talk, but let me just tell you what chapter and what page to read again. Chapter 13. Chapter 13. Chapter 13? Yeah. Chapter 13. 13:9. I don't know if this. You don't have to read this whole section. Well, why is it so slow? Yeah, otherwise I wouldn't have done it if I had known this would take this long. I just wanted you to read from here, interionic attractions, down, which is about a page and a half at the most. I asked you to do this when we're talking about activities because activities were first discussed in chapter 13. This is the table, we talked about this table, sodium chloride versus magnesium sulfate. Magnesium sulfate is much worse because of the 2 plus and 2 minus. And then we had lead 2 nitrate, which is going to be bad as well. And so these do not behave independently of one another, which means they do not behave ideally because, ideal solutions should be behaving independently of each other. And then we call this the activity. And so when we talk about, we should be using activities, right? We should be using activities, but we aren't. We're using the ideal concentrations. For every mole of this, we get 1 mole of this and 2 moles of that, right? That's ideal. But in reality, there could be other species, like a calcium linked with 1 fluoride, floating around. Now, those other species are going to change the activity of the calcium ions and fluoride ions. And those things we should compensate for, but we aren't. And so what this means, the whole point of this is this. When we start getting these higher charges, then you should start expecting more error in your calculation. And so the take-home point is the higher the charge, maybe the more. And also we are completely ignoring ion-paired species. Ion-paired species would be like, ion-paired species would be like why HF is such a weak acid. HCl, HBr, HI are strong acids. Why is HF such a weak acid? is ion pairing. Right? Chapter 16. I skipped that entirely because I covered that in Chem 1A. I think. Did you guys cover that in Chem 1A? Well, Chem 1A is so long ago. I know you guys. Do you guys remember that, Jasmine or Jameson? Probably not. It's a while back. Yeah. But the thing to do is, once in a while review that, and then it's fresher in your mind. So you'll remember. Okay, with that said, we're not going to do activities for any of these. And so even if it's a 3+, I don't care. If it's a 3+, where we expect, 3+ cation, you're going to expect some ion pairing type interactions. You're going to expect some deviations from ideal behavior. You're going to expect that the activity, actually, where was that activity? Yeah. You're going to expect that the activity or the effective concentration is going to actually deviate quite a lot from what we have, the ideal concentration. And so in the back of your mind, you just think, okay, there's going to be greater deviations. The same thing you do for the ideal gas law. The more the gas deviates from an ideal gas, the more error you're going to have in your calculation. Well, all we're doing are the ideal gas law type calculations here, right? We aren't doing real. We're just going to stick with ideal. But that doesn't mean you should ignore the real behavior. Okay, so anyway, getting back to this, then if that's the case, then the KSP for this, actually run out of room here. Let's write the KSP for this is 5.3 times 10 to the negative 9. Thanks. Is that from our book? Yeah. Okay. Shoot. Wikipedia is way different. Wikipedia is 3.9 times 10 to the minus 11. I don't know.
25 degrees Celsius.
I don't know who's right. I don't know where the value for Wikipedia came from, but there's a footnote here.
From McGraw.
2002?
That's so
Yeah, 2002 is pretty old. Our data, I think, is a little more up to date. So we'll go with this. Which one is bigger? This one's bigger. This has a bigger KSP, so this one should be more soluble? Yes?
Yes.
No, we don't know. Why don't we know? Because it's nonlinear. The solubility here is the square root of the KSP. The solubility here is, let's take a look. This is 0 molar. And this is 0 molar. So we assume nothing's dissolved. And now we're going to let it dissolve. So this is going to be plus S molar plus 2S molar. And so at equilibrium, we're going to get S molar and 2S molar. And so what this means is this. The KSP is equal to the calcium ion concentration here times the fluoride ion concentration squared. And so the calcium ion concentration is S, the fluoride ion concentration is 2S quantity squared. This gives us 4S cubed. And so the solubility here is going to be the KSP divided by 4, and then you take the cube root. And so what happens in this particular chapter is sometimes these comparisons are difficult because of the different exponents here that we have. And so sometimes you can be fooled into thinking something's more soluble when in fact it's actually less soluble.
Okay, however, if it was something like NaOH and NaOH had a bigger KSP, then NaOH would be more soluble, right?
Yeah. Well, NaOH, the tricky thing about NaOH is we're never going to do NaOH. Is the reason we aren't going to do NaOH is because is it infinitely soluble? NaOH is soluble because all sodium salts are soluble. And so if we're doing NaOH, will we just do this? NaOH dissolves completely. It's one way. K is very, 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 very large, and it just goes one way. Is that what we do? We have solid NaOH. So in other words, if I had 1 billion grams of NaOH and I wanted to dissolve that 1 billion grams in 100 milliliters of water, no problem, because it's one way. Would that work? No. Even sodium chloride. Sodium chloride, you know, most people think of sodium chloride as being extremely soluble, right? Salt in water. But sodium chloride has limits. Sodium chloride solubility is more like 36 grams per 100 milliliters, max. If you try to go more than 36 grams, it isn't going to dissolve, right? The extra. And so it's not infinitely soluble. And so salts like this, we should generate a KSP for, because sodium hydroxide is not infinitely soluble. We're going to get some kind of KSP number here, right? And then we can do the calculation. It's going to be a huge KSP because it's pretty soluble, but it's not going to be infinite. That is, there is a limit to how much you can dissolve. But you'll notice this whole chapter deals with insoluble salts. What about the slightly soluble and the soluble salts? Why are we ignoring those? One of the reasons we're ignoring the soluble and the slightly soluble we might do, but the soluble salts, one of the reasons we're ignoring that is because they behave more ideally, and therefore we don't need to do it, or they behave so far from ideal that the calculation that we get is so far off, we might as well not even bother. The opposite of that? Well, one of the reasons we don't do the soluble species is because the calculations are just too far off. They're going to be too grossly in error because they're going to deviate so far. You know, the concentrations are so high, right? Well, anyway, yeah, as the concentrations climb up or as the charges climb up, then we're going to expect larger deviations, and therefore our calculations are going to be off. A rule of thumb for some of these calculations is, and this is in this chapter, you know, you can expect up to maybe 10-15% error because of this assumption. You know, but that error can be quite small. You know, the error can be small if you expect it to behave pretty ideally. Nonetheless, the calculations are useful, you know, even if there is this error of using these ideal concentrations versus real concentration. And so here, let's see, the solubility, we can calculate it. You know, it's pretty easy to calculate the solubility. Just divide that by 4, take the cube root. Here, it's even easier to calculate the solubility. These are molar solubilities. Right? We can calculate the molar solubilities easily. Or, if we know the solubilities, you know, then we can plug the solubilities in to get KSP. Now, what is this really the solubility? When I look at S is just the silver ion concentration. How come this is the solubility of this? And so, the reason is it's because of this. The solubility is defined as how many moles of silver chloride dissolve, not how many moles of silver. But we know that silver chloride and silver are in a 1-to-1 mole ratio. And so it's going to be the same. That is, the molarity of silver, in this case, is equal to the molarity of chloride, which is going to equal the molarity of silver chloride that dissolves. And so how many moles of silver chloride formula units actually dissolve? Well, that's going to be S. And these are all equal to S. Over here, is the solubility the concentration of the calcium, or is it the concentration of the fluoride, or both? It's only the calcium concentration. Because for every calcium, we had to have one CaF2 dissolve. Well, if you have one CaF2 dissolved, we are going to get 2 fluoride. So the fluoride concentration is actually double the solubility. Because the solubility is defined as how many calcium fluoride units can we dissolve. How many moles of these units can we dissolve per liter. And so the calcium is in a 1-to-1 mole ratio, therefore it's the same. But this is not. So that's different. All right, so the basic calculation is this. You know, it's either going from KSP to S or S to KSP. And so these are the calculations we do. So what you can do is you can look up in a KSP table. There are lots of KSP tables around, including the one in our book in Appendix D. Let's take a look at a KSP table here. It's not in Wikipedia. Sorry. So we got a bunch of KSP tables. That means, what can we do with all these KSPs? We can calculate the solubility. If that was all there was to chapter 18, then you'd be lucky, because that's a pretty easy calculation, isn't it? You'd be lucky. But chapter 18 turns out to be the hardest of the equilibrium. But fortunately, it's the last, so it's not going to get any harder than chapter 18. This is the hardest it gets. What makes it so hard? It's because we want to see, what types of things influence the solubility. For example, calcium fluoride, like I said, is more soluble in acid. Well, I want to know, what is its solubility at pH 4? What is its solubility at pH 2? What is its solubility at pH 1? Those types of things. Or simple questions that were from the lab. Like precipitation. And so the first type of calculation we're going to do is influencing the solubility via the common ion effect. I can change the solubility by introducing a common ion. And so we could use either calcium fluoride or silver chloride. Which one do you want to do? It doesn't really matter. Let's do calcium fluoride. And so if I have some calcium fluoride here, and I want to decrease its solubility, is there a way to do it? Well, it turns out there's an easy way to do it, and that is I can add something. Like, for example, if I add some fluoride in here initial, but this fluoride doesn't come from calcium fluoride. This fluoride is going to come from some other salt. What's a soluble fluoride salt? Maybe like sodium fluoride. And so if I pour some sodium fluoride in there, am I going to get as much calcium fluoride to dissolve? And so we start up this with a standard ice calculation like this, where we say none of it's dissolved yet. And so there's 0 molar calcium because no calcium fluoride is dissolved, but we do have fluoride present from some other source. What's this going to do to the solubility? Will the solubility of calcium fluoride be the same, less, or more?
Less.
It's going to be less, as you know, because we know the common ion effect already, right? If we got common ion there, we aren't going to generate as much calcium, therefore we aren't going to dissolve as much. And so it's the same thing. Is this plus S or plus X? Plus S molar, this is going to be plus 2S molar. And so at equilibrium, I'm going to get S molar, and then the fluoride initial here, which we have, plus 2S molar. And now when I solve for S, S is going to be a smaller number than before because of the common ion effect. And the more common ion I have in here, the less calcium I'm going to have. And so there's a way to minimize the solubility. If I don't want any If I don't want any calcium fluoride to dissolve, I'll just maintain a very high concentration of fluoride. Very high concentration of fluoride here means, only a minute fraction of calcium can be generated before it's attacked by the fluoride to form calcium fluoride. So we talked about this many times. Common ion effect. Well, this is the same kind of concept as in precipitation. So here, etc. S is less. So the common ion effect is used in precipitation. And so let's look at precipitation as an application of this. But in precipitation, let's say we wanted to precipitate out calcium. You precipitated out calcium ion in the lab using hydroxide. No, actually we didn't, did we? What did we use to precipitate out? Calcium hydroxide is soluble. Did we use to precipitate out calcium in the lab? Oxalate. Was it oxalate? A lot of people mix up oxalate with chromate. I think it was oxalate. In fact, I'm sure. And so here's what we want to do. Let's say we have some calcium ion in here. And let's say I have 0.100 molar calcium ion in here. Then if I want to precipitate out my calcium ion, then I add drops of oxalic acid, but I'm not going to add oxalic acid. I could also precipitate out the fluoride. So I'm going to add fluoride ion. Maybe from sodium fluoride. We don't have fluoride. Did you notice fluoride's missing in our lab? Why? Because actually both are bad. The fluorine chemist handshake is like this. The fluoride actually, let's see if that matters. Is HF a strong acid or HF a weak acid?
Weak acid.
Oh, these are censored pictures. HF hazard. This is fluoride. It's not because of the acid. It's because of the fluoride. HF burns. How about that?
Nice.
Yeah. Oh. Yeah. Do you see that? That's not like spilling acetic acid on your hand, is that? No, or eating a little bit of vinegar. This is ooh. Sorry for the gruesome. So both fluorine and fluoride are nasty stuff, So stay away. It's fluorine because it's a powerful oxidizer, and fluoride because it's a nasty metathesis agent that can. In fact, I heard about you hear about it because HF is used to etch semiconductors. So in the electrical engineering department, they have the wall of horrors there. But if you spill HF on your flesh, it doesn't really burn like concentrated HCl or nitric or sulfuric, And so it's a mild acid. What it does, and it doesn't really react too much, although it could cause burns like that in time. In time it will start eating things away. But what happens is it penetrates the flesh because your flesh is like a sponge, and then it hits your bone. When it hits the bone, it starts precipitating out calcium fluoride. When it starts precipitating out calcium fluoride, I've heard it's extremely painful. So it's not just like amputating a finger. How do you get it off? How do you get it off of you when it's already penetrated your flesh to the bone? And so I guess you could wash for 15 minutes, but it's probably not going to do you much good. And so I heard about these, and it can lead to death, basically, because it causes so much trauma there. with that. And so, at these places where they do use a lot of fluoride, you know what they have? They have calcium glutamate injection kits. And so if you get too much fluoride, you're supposed to inject yourself with calcium glutamate to lower the fluoride concentration in your blood. Something like that. Well, anyway, so we could use fluoride to precipitate out calcium, right? And so how would we do this? We just keep adding, right? Keep adding fluoride to precipitate out the calcium. That's it. Simple as that. And so we just did that, but sometimes you have to worry about this happening. So I should have left these up. Sometimes you have to worry about these precipitations because of complex formation. So for example, when you were doing copper yesterday, what happens? If you want to precipitate out the copper, you used ammonia. And you got this light blue precipitated copper 2 hydroxide. And so you just keep adding the ammonia, and the amount of precipitate grows until, what happens? Until you keep adding, and the amount of ammonia amount of precipitate decreases until it disappears, right? And so the typical precipitation, we just keep adding. The more fluoride we add, the more calcium we should be able to precipitate out. As long as there's no complex formation, or the complex formation is not so significant. In silver, there is complex formation. This is the typical precipitation for silver. Silver nitrate plus sodium chloride. In this case, they're using sodium chloride. We couldn't use sodium chloride because sodium is one of the unknowns. And to precipitate out silver chloride. But if we keep adding chloride, what can happen? If we keep adding chloride, the chloride eventually attacks the silver chloride precipitate and dissolves it. So this reaction here wasn't so bad. This one is not as favorable. The one for copper is much worse. When you attack the copper 2 hydroxide, which is light blue precipitate with ammonia, you form the tetramine complex. And so this one, the amount of dichloroargentate, one that's formed is minimal there. So this is why I said just keep adding. Because I know in this particular case you don't have to worry about that. Well, the same thing here, we aren't going to worry about any complex formation, we're just going to add more fluoride. And so what I want to do here is a calculation. I want to calculate how much fluoride is required to precipitate out all my calcium. I just don't want to add drops. I want to do a calculation to figure out how many drops I need to add. This is better. That way it's not a mystery, As the book might say, 4 drops, but you end up adding 20 drops and still it's not there. And so let's take a look at this particular problem. So I have calcium chloride, solid. This is going to go to calcium ions and fluoride ions. And so basically I have now I have 0.100 molar calcium 2 plus. So if I have 0.100 molar calcium 2 plus, how much fluoride do I need to precipitate all that out? You would think 0.200 molar should be required.
Why 0.200?
Because we need twice as much fluoride as calcium. Just stoichiometry. In Chem 1A, it would be 0.200 because just go 100% backwards and we'd be left with 0 and 0, right?
Yeah.
But let's see about Chem 1B here. So this is a little different.
Can't we just overshoot it?
Yeah, we could always overshoot everything, but the problem with overshooting is sometimes you run into this. Sometimes you won't run into a problem where too much is not good because you're going to lose a little bit of precipitate. And so if we want the maximum amount of precipitate, then we should just hit it right on and not risk forming any kind of complex ion. Like copper, just overshoot it. If you want that light blue precipitate, just keep adding ammonia, and then what do you see? It's gone. Right? And so what we're going to do is we're going to be at least a little bit more precise in this, and a little bit more accurate in trying to determine it. And so initially there's 0.100 molar calcium, and now I have 0.200 molar fluoride. This should precipitate it all out, right? Should be required to precipitate all the calcium. All right, so what is my change going to be? What was the KSP again? 5.3 times 10 minus 9? Is that it from our book?
Yeah.
Okay. What's the change going to be? Is it going to be minus 0.100, minus 0.200? Goes fully in the reverse direction? One-way reaction. Is this a one-way reaction? No. The change is going to be minus, it's got to go backwards, I think. Minus x, or s. Minus x, minus 2x. And so at equilibrium, we're going to get 0.100 minus x, 0.200 minus 2x. And just solve for x. So solving for x, the KSP is going to equal the calcium ion concentration times the fluoride ion concentration at equilibrium squared. So this is going to be 0.100 minus x times 0.200 minus 2x squared. What should I do next? I know. Should I try the simplifying assumption? SA? SA barely takes any time. Should I try it?
Yeah, why not?
Why not?
Oh, 'cause it's-
Why not?
so that's-
Because I know it's not going to work. Why do I know it's not going to work?
5.3 to negative 9.
Because this K value tells me that the equilibrium should consist all reactant or all product. A very small K value tells you to expect all reactant. And therefore, we expect this to be a big change in the reverse direction, a small change in the forward direction. And so I know that the SA won't work here because the change in the reverse direction is going to be huge. If it were plus x and plus 2x, I'd say, yeah, for sure, do the SA, because we expect a very small change in the forward direction. Does that make sense? Okay. So what do I guess, do you have a calculator? Do you have the calculator that does the cubic equations?
Yeah.
The Casio? So you can get this into cubic form. Ax cubed plus bx squared plus cx plus d equals 0, and then plug that into your calculator. If you don't have that calculator, you could solve this using successive approximations, right? Guess and check. Do that, right? Or you can do what? Skip the question. Work on something, yeah. I guess you could skip it. I guess this is the problem. When you have chapter 17, you don't do all the techniques. 17, the worst you had to deal with was quadratic. It's not too bad. 16, the worst you had to deal with was quadratic. 15, you had to deal with more difficult. And so what did we do? Can you think back to 15? Reset. Yeah, you know, I wouldn't have even gotten this far. I would have seen these and I would have thought, this is too difficult. Let's just reset it. Reset left. And so if we reset this to the left, what are the new initial? This is going to be 0 and 0 and 0. Is that right? Did we just lose atoms there? You know, atoms are neither created nor destroyed, so did we just violate that? No, we didn't violate that, because do you know where all the atoms are now? All the atoms are in the solid. And so they're still there. It's just now, it's like if you have 100 gallons of water. You had 100 gallons of water on the right, and then you push it all the way to the left. If you push all 100 gallons to the left, you're going to be left with 0 gallons of water on the right. But all the 100 gallons are still there. They're just over here now, right? And so this is correct. It's a 0 and 0 to reset it. Now the change. What is the change? Plus S plus 2S. And so at equilibrium, we're going to get S and 2S molar. All right, now look at the math. If we compare it, this is going to be S times 2S quantity squared. Which is easier, solving a cubic or resetting it and solving this? Resetting it and solving this is way easier, wouldn't you agree? I don't know if there are any people who still refuse to reset. Anyway, this is going to equal 4s cubed, which means that s is equal to
1.09 to negative 3.
1.09 times 10 to the negative 3. Huh. Did we precipitate out all the calcium? We started with 0.100 molar. Did I precipitate out all the calcium?
No.
No, there's still some remaining. I want to get rid of that. How can I get rid of that remaining bit? Because you know what? I want the maximum amount of precipitate.
Push more flow.
So I add more fluoride, assuming no complex forms. That's perfectly safe. And so how much would be required? Now I'm going to overshoot it, because my goal is to precipitate out all the calcium. And so how much fluoride is going to be required to precipitate out all the calcium to get the maximum amount of precipitate? Well, this is 0.2. We tried fluoride. So we're going to add more fluoride. So what should I make the initial concentration? Should I just go for double this? Is that enough? So rather than 0.200, let's go 0.400. That should be overkill or maybe not enough.
When is it going to be enough? If we're in like the negative 7, negative 8, is that enough?
I don't know. I want 0. I don't know. Maybe. It depends on how you define it. And so let's try bigger value of fluoride. What should we try? And so there's still calcium left over. Unprecipitated. We call this the calcium ion that remains. And so if something calls for 20 drops, then 40 drops must be better, right? So let's just double it. Should we just double it? Or maybe we should go tenfold. If it says add like 20 drops, maybe I'll just get the grad cylinder, the beaker, and just dump it in there. That would be better, wouldn't it? Assuming that no complex forms, what should I bump this up to? Should I just double it, or should I tenfold, or what do you think would work to get the maximum amount of calcium out?
One mole? 1 mole?
1 molar? So 5 times as much than what should be required. I mean, 0.2 should be required because that's a stoichiometry. So we're going to go 5 times more? 1 molar? All right. Do that. And so I'm going to just start this problem over again. And here I'm going to go 0.100 molar. I'm trying to precipitate this all out, 0.100 molar. But this time I'm just going to go this, 1.00 molar. That should precipitate it all out, right? And so what is the change going to be here? Minus x minus 2x.
Should we just reset already?
Should we just reset it already, or should we go through this?
Why waste your time?
Why waste the time? Yeah, I just reset it, right? No reason to generate that. And so if we reset it, what should it be? Here, reset.
0 initial for both.
0 initial for both? 0 molar and 0 molar? Thanks.
Yeah, but it just keeps giving us the same thing each time.
Yeah, if it were 0 and 0, we'd get the exact same thing, but it's not 0 and 0 molar. It's 0 molar and something else. What is that something else? No, it's not S. Do you guys remember the reset? I skipped this step. I skipped this step because I thought, oh, you guys can do this in your head or by now because you're pros at resetting, right? Are you pros at resetting? Remember resetting? Minus y minus 2y. We look at what's the limiting reagent? It's calcium. So this is the limiting reagent. Limiting reagent is consumed, completely going backwards. So y is equal to 0.1. 2y is equal to 0.2. Therefore, this is 0.98. Oops.
Wait,
0.8.
no,
0.8. Sorry. 0.8 molar. 0.80 molar. Is that right?
Yes, makes sense.
Yeah. And so this is reset. And so do you see this? This means that we're going to have, in other words, we're going to have a lower solubility, which means if we have a lower solubility, that means we're going to get more precipitate, right? Uh-huh.
I'm kind of confused how you knew that you still had CO2 plus left.
How I do this? The
No,
reason-
how you knew you still had some CO2 left.
Oh, because I calculated the equilibrium conditions here using KSP. And so, why didn't we go 100% reverse? The only time we go 100% reverse is if KSP is very small, literally, that we have no number for this. It's like up there. Do you see the strong acids? Look at the strong bases. Very small in the forward direction. If it's very small in the forward direction, do we expect the forward reaction to occur? No. If it's very small in the forward direction, we expect the reverse direction to be very large. And so the reverse reaction occurs. And so the only time would be that. But if we have a number here, then we should calculate the equilibrium concentrations. Yeah. And so all I did was I calculated where this ends up. Because we can't assume that. Can we assume that this is going to be plus? Well, what can we assume it's going to be plus? plus what? And so when we reset this, then we're back to a regular ICE type problem. So here, but this is, do you recognize this type of problem? This is called a common ion problem because we have this, and therefore the solubility is going to be smaller, which means that more precipitates. Because the less soluble it is, the more precipitates. And so at equilibrium, this is going to be S molar, this is going to be 0.80 plus 2S molar. And so now we're going to do the calculation. KSP is going to equal S times 0.80 plus 2S quantity squared. Well, we'll come back to this again, the previous problem. But for right now, will the simplifying assumption work? Yes or no? Yes. The simplifying assumption should work here, no problem. Why? Because now we're going in this direction, right? When we go in this direction, K is small. If we go in the reverse direction, K is large. And so since we're going in the small direction, the simplifying assumption should be no problem. So this is, and then S is equal to if you ever go back in your notes and you look at when we were talking about resetting, one of the purposes I said for resetting was so to make the simplifying assumption more likely to work. You know, that was one of the goals in resetting it, was to get the simplifying assumption to work.
8.281
Times 10 to the negative 9. And so this is 10 to the negative 1, 10 to the negative 9 gives me 10 to the negative 8, times 10 squared gives me 10 to the minus 6. So this is a 10 to the minus 6% change. A 10 to the minus 6% change means that if we solve this cubic using our fancy calculator versus doing this, we're going to get about the same answer. Pretty much the same answer. I mean, the essay is totally valid in this case. And so now it's down to 8.28 times 10 to the minus 9 molar. And I'm not going to bother calculating that. But did we precipitate out all the calcium, or do we still have some remaining?
We still have some remaining.
We still have some remaining. And so 1 molar wasn't enough. What should I do next? What should I change it to?
When is enough?
19 molar.
What, you tell me when is enough. What molarity do I need to precipitate out all my calcium?
If it's at 10 to the negative 12, is that insignificant enough?
I want 0. I want 0 calcium left. I don't want any calcium left. I want all precipitate.
What if it was like 8.28 times 10 to the negative like 500 is that? That's okay.
No,
That would be
that's
zero.
getting better. That's getting better, but negative 10 to the negative 500 is still far away from 0.
We can't please you.
Yeah, why can't you? I mean, because actually, what is it?
Well, shouldn't you be using initial concentrations instead of these concentrations, because, or the equilibrium concentrations? Won't that affect like how much precipitate you get in
All right, I'm running out of time here. I didn't talk about this. But basically, you know the answer I was looking for? How much fluoride do you need to precipitate out all the calcium? Infinite. You know, it's taken us a long time to get there, but we would need infinite to precipitate out all of it. And so the question is, how much is enough? Well, how much is enough depends on how much percent we precipitated. For example, if we precipitate out 99.999999% of the calcium, is that enough?
No.
Yeah. Well, is this enough? Did we precipitate? How much did we precipitate here? And so the amount that we precipitated, percent precipitation, equals the percent remaining, 100% minus the percent remaining, sorry. That's the percent precipitation. And so to calculate the percent remaining here, the percent remaining, let me just write this equation and then I'm done, is equal to the equilibrium concentration over the initial concentration. Now we have two initial concentrations. Whenever we reset, we have the reset initial versus our original initial. And so in this case, which one would we use? We would use the original, not the reset. But the original is always after solution dilution, but we didn't have solution dilution here, times 100%. And so we'll talk about this next time. In fact, we'll just do the calculations for this next time and then go to the next section after that.